So we are officially starting our notes now on our probability unit. So first, just to define what probability is, we are starting. Thank you. The probability is the likelihood of a random event. So we're just figuring out how likely an event is to occur. That is the probability of an event. So a sample space is when we list all of the possible outcomes from whatever experiment you're doing. So like if you're rolling a die, you'd be listing all the possible outcomes you could get from rolling a die. So a list of all possible outcomes of a probability experiment. And when we define a sample space, we use a capital letter S to denote sample space equals, and then we use these fancy brackets, and you would just list all of the outcomes in between those brackets. Do your best to draw them. Squiggles are fine. All right, and then an event is a subset of that sample space. So it's a specific event or a specific outcome or outcomes that you are looking for when you do this experiment. So a subset or a smaller group of outcomes from a probability experiment or from the sample space. So when we are defining an event, we use a capital letter E, or when we have multiple events that we're talking about, it's any other capital letter besides S, because S is for sample space. So events can be denoted by any capital letter, and then we still use those fancy brackets, and we would list the event in those brackets. Okay, so an example of defining these: if our probability experiment consisted of us rolling a die, so a fair 6-sided die, if we wanted to define the sample space, we'd have S equals. And then I just have to list all the possible outcomes. So when I roll a die, what are all the possible outcomes I could get? Yeah, 1 through 6. I could get a 1, 2, 3, 4, 5, or 6. So you just list 1, 2, 3, 4, 5, 6. So sample space is just what could happen. Okay, and now when we're defining an event, now we are looking at specific outcomes from that sample space, and that's what we're looking for. So in this case, for letter B, we want to define the event of rolling an even number. So when we are defining this event, if we roll a die, what outcomes would fall into that category of an even number? 2, 4, 6. So that would be our, when we define that event, would just be 2, 4, and 6. Okay, so sample space is everything that could possibly happen. Event is specifically what are we looking for in this event. Any questions there? Okay. All right, so now the two main rules of probability. The probability of any event must be greater than or equal to 0 and less than or equal to 1. So that means we can't have any negative probabilities, and we can't have any probabilities that are bigger than 1. And we use this notation P of x to denote the probability of x. And then when we have the probabilities of all of the events in our sample space, the sum of those probabilities must equal 1. So if we add together all the probabilities from a probability experiment, they have to equal 1. Okay, so example 2, if we want to verify that this is a probability model, this is asking you to see if that probability model follows both of those rules of probability. So this is asking, does it follow the 2 rules? So we have these 2 rules listed here. This table, this was the outcome, so rolling a 1, 2, 3, 4, 5, or 6, and this was the probability of rolling those, just based on an experiment. Okay. So number 1, the first rule, again, we have to make sure that out of all our probabilities, we don't have anything that's negative, and we don't have anything that's greater than 1. So are all of our probabilities okay? Are they all in that range? Yes. So yes, we're good there. Follows rule number 1. And then rule number 2, we have to add up our probabilities and see if they equal 1. We add them all up. And I think it does, 1.0. So since it follows both rules, then yes, it is a probability model. If it has to follow both of them, so if it follows one rule but not the other, then it's not a probability model. Both things have to be good in order for it to be a probability model. All right, so today we're going to be focusing on classical probability. It's also called theoretical probability. So these 2 terms or names are used interchangeably, so make sure you're familiar with both of them. Classical probability is just when we use counting techniques to calculate the probability of what should happen mathematically. Okay, so classical or theoretical probability is theoretically what should the probability be. So like if we're flipping a coin, theoretically it should be 50-50. However, if you flip a coin 10 times in a row, that does not necessarily mean you're going to get exactly 5 heads and 5 tails. So the classical probability is what should happen, just based on the numbers. Okay, and then equally likely outcomes, as the name kind of suggests, is just when we have outcomes who have the same probability of occurring. Okay. Outcomes with the same probability of occurring. So many probability experiments have equally likely outcomes, like rolling a die. All 6 sides of a die are equally likely to occur or to show up when you roll it. Drawing a card from a deck of shuffled cards, each one is equally likely. Okay, so to calculate this classical probability, we're using the classical method. If we want to find the probability of event E, so again, that's what this means, probability of event E. Then we take, in our denominator, we're going to have the just total number of possible outcomes, so the number of things in your sample space. total number of possible outcomes goes in your denominator. And then your numerator is the number of ways event E can occur. So that'd be the number of outcomes in your event that you define. Okay, and then when we are calculating these probabilities, we can keep our answers either as decimals or non-reduced fractions. I know you guys have been taught to always reduce fractions if possible, but with probability, if you don't reduce them, it makes it easier for me to see where you're getting your numbers from. So for the purposes of probability, it's okay if you don't reduce fractions. Keeping it as is okay. Okay, so example 3 now, calculating these classical or theoretical probabilities. If we have a bag of marbles that has 4 green, 3 red, 5 blue, and 2 orange marbles, when one marble is drawn, we want to find the probability of drawing a blue marble. So if we want to find the probability of blue, then that's going to equal, in our denominator, it would just be the total number of possible outcomes, which in this case would be the total number of marbles. Then our numerator would be the total of ways event E could happen, or the total ways we could draw a blue marble, which would just be the number of blue marbles. So in this bag of marbles, we have 5 blue over 14 total. 5 over 14, and it's fine to leave it as 5 over 14. If you don't want to do a decimal, that's fine. If you do, you just type 5 divided by 14 in your calculator, hit enter. That would give you the decimal. Okay, letter B, the probability of not drawing a green. So the probability of not green. So our denominator is still going to be the same. We still have 14 total marbles to choose from. But now for our numerator, how many ways is it possible for us to not draw a green marble? 10, because there are 10 marbles that are not green. So 10 over 14. And again, you can leave it as 10 over 14. You don't have to reduce it to 5 over 7. Okay. Can you guys try C and D? So probability of drawing a red or orange, and then determining which one's more likely, drawing a blue or a green. Okay, so for letter C, probability of red or orange. What number was in the numerator of your fraction? How many red or orange marbles are there? 5. We have 3 red plus 2 orange gives us 5 over our total number of marbles, which is 14. Questions on C? Then letter D, which one is more likely, drawing a green marble or drawing a blue marble? Blue. Why?
Because it has more marbles.
Yeah. More likely because it has more marbles, which means a higher probability. All right. So classical theoretical probability is pretty straightforward. It's just taking the numbers mathematically what should happen. So on the back or on the next page here. So interpreting probability, we kind of did a little bit of this in that last question, determining which one is more likely. If an event is impossible, what do you think its probability would be? On a scale of 0 to 1. 0, yeah. But if an event is impossible, that means there's no chance that it can happen. So its probability would be equal to 0. If an event is certain, so you're 100% sure it is going to happen all the time, no matter what do you think that probability would be? 1. Meaning it's the only option, it's the only thing that can happen. So this is our scale, 0 being impossible, 1 being certain. So on that scale, the closer to 1 the probability is, the more likely it is to occur. Okay, so example 4, we have a bag of M&Ms. Colors can be brown, yellow, red, blue, orange, or green. So suppose that candy was randomly selected from the bag, and the table below shows the probability of drawing each color. So they already calculated the probabilities for you. So letter A wants us to verify that the data is a probability model. So remember, it has to follow those 2 rules. 1, that all of our probabilities are between 0 and 1. So does that model follow that rule? Yes, we don't have any negatives. We don't have anything that's bigger than 1, so that one's good. And then we need to make sure that they add up to 1. So if we add up all of these probabilities, do we get 1? Yes, we do. So since it follows both, then yes, it is a probability model. Okay, so what would we call the event green, drawing a green M&M? Since its probability is 0, what does that mean? It's impossible. So what does that mean about the assortment of M&Ms that you have? How many greens are there? 0, because it's impossible to get one. That means there can't even be one. So that means there are no greens. Okay. So this last one, letter C, computing the probability when I'm already giving you a probability model that has each individual probability calculated. It's pretty straightforward. You just have to pick out the specific events that we want and add them together. So the probability of event E, drawing a brown, a red, or an orange M&M, just means you would take those 3 probabilities, 0.15 plus 0.19 plus 0.22, and add them together. What do we get when we add those? 0.56, I think. Yes, correct me if I'm wrong. I think I'm right. Okay, you're just going to trust me. Cool. All right. Do you guys have any questions so far? Well, I guess this is the end, so no so far. Okay.